at the quantum mechanical model, quantum, if you look at the carbon atom, now the carbon atom has what? It has 6 protons, right? 6 neutrons for carbon 12, and 6 electrons. So the 6 protons are going to be inside the nucleus here, and the neutrons. You got the protons and the neutrons in the nucleus. So what's happening with electrons? What's happening with electrons is, you know, what Bohr would have said is, Bohr would say that the electrons are orbiting. So we have 6 electrons orbiting around the nucleus. Etc. Is the Bohr model correct for that? No. So the Bohr model, this is wrong. And so how do you visualize the electrons in a carbon atom? Well, if the nucleus is here, then the way we visualize electrons is we're going to have, in the carbon atom, this is the quantum mechanical model here. In the carbon atom, we're going to have what? Well, we can figure out where the electrons are based on the energy level diagram. So what does the energy level diagram start with? 1s. And how many electrons are there in the 1s orbital? 2. And so how should I draw the 1s orbital? Well, one way of drawing the 1s orbital is by either a sphere or what's this called? When I draw these dots on here, what do I call that? What do the dots represent? They don't represent individual electrons, they represent the probability. And so I'm going to have a 1s orbital here. Call that the 1s orbital. And the 1s orbital is going to have 2 electrons. So one electron is going to be spin up, the other electron is going to be spin down. So I have 2 electrons there in the 1s orbital. Okay, then I move up. After the 1s orbital, then the next allowed energy for the electrons will be the 2s. And so how does the 2s look different than the 1s? 2s is bigger or smaller? Bigger. 2s is higher in energy, bigger. So 2s is going to be like this. 2s orbital. And the 2s, when we look at the probability distribution, the probability distribution spreads out more because it's higher in energy. You're going to get some different probability distribution, but I don't have enough colors to start. So this is a 2s. How many electrons do I have in the 2s? 2 electrons. So we can put those in here. Can we pinpoint the electrons? No. Can I know exactly where the electrons are in the orbital? No. That's a result of what principle? Heisenberg inserted principle. We can't pinpoint exactly, but I know I have 2 electrons that have the energy of 2s. Okay, after the 2s, then what do I have? I have the 2p orbitals. And how many 2p orbitals are there? 3. Okay, well, that's 2, 4. I only have 2 more electrons, so how do I fill these? 1 at a time or 2 at a time? 1 at a time. So I got 1 electron in the 2p. And so the 2p orbitals are like this. I have a choice. I could put it in, this is which one? Whichever. I could put it in, the only difference is what axis this lies on. This one's on the z-axis here, the z. This one's on the x-axis here. And then I have one more. This one's along the y-axis here. And so they're the exact same shape. They just don't, only different how you orient them in space. So we have 3 of these. It doesn't matter which one I pick. Usually people just pick the first one. So how should I draw that here? Well, I'm going to draw it like this. going to draw a p orbital. It has two lobes, like this. And the electron can be either in the top lobe or the bottom lobe here. This is the Z, let's say. And so I can pick one of these here. It doesn't really matter. I'll just put it up here. They have one electron spin up like that. Okay, so this one is a half-filled p orbital. And then I got to pick another p orbital. So I'll just pick the one that's coming out like this. Or maybe I'll pick the one to the side here. But I should try to make it look a little different. So it should be used a different color. It's not squiggly like this. I'm just writing it because I'm using black pen both. And so these two lobes belong to the first p orbital, and these two squiggly lobes belong to the second p orbital. The second p orbital is going to have one electron like this, and so we can just throw it in. It's also going to be spin up. And so this kind of the now when I look at the probability here, the probability here, probability here, probability. This kind of gives us a map. Well, it does. It gives us a map of how the electron is distributed. The electron density or the electron cloud is distributed in the atom. And so what ends up happening is it looks kind of like this. You know, this is all three p orbitals and a 2s. So I got my 2p. There's a 2pz up here. You can see just the top of the lobes. The 2px right here, and the 2py, which is coming out. And then the 2s, which is the sphere. Electron clouds there. Kind of has a spherical symmetry. So this is it here. This is descriptive. This is called an energy level diagram, but we also have electron configurations. Electron configuration is not going to be as descriptive. 1s2, 2s2, 2p2 electrons. A cross between the energy level diagram and the electron configuration is called atomic orbital diagram by our supplement. Atomic orbital diagram is kind of a midway between these two. This one takes up a lot of space because you got to write this vertically. This one takes up not that much space, but we lose some information on the electrons. In an atomic orbital diagram, it's kind of a compromise. So we draw a box 1s, another box with a 2s, and then 3 boxes that are joined together for the 2p. And then we'll fill these here. And so in an atomic orbital diagram, we could see, we have 2 unpaired electrons here, which we don't really see based on the electron configuration. So this is kind of a compromise, the atomic orbital diagram. A hybrid between the energy level and the electron configuration. And so these are very common because they don't take up much space and they give us more information than electron configuration gives us. Those are useful to have. All right, and so they're just the, how do you figure out the orbitals? We figure them out using the quantum mathematical restrictions. Okay, now, that's pretty much it for chapter 11, and the supplement. The supplement goes into more depth with quantum numbers. There's some homework problems on quantum numbers in the supplement, and there are also homework problems on the periodic table. Okay, let's take a look at the next chapter, chapter 12. Chapter 12 deals with chemical bonding, when we put the atoms together. And so now we have the atoms, we have kind of an idea of how the electron cloud is distributed. We have an idea of some of the properties of atoms as well. And so when we're talking about bonds, chemical bonds, we have types of bonds. Actually, not all the chemical bonds behave in the same way or share the exact same characteristics. They're all electrical, and so all bonds are electrical attractions in nature. And so electrical attraction is just positive being attracted to negative. It's just how the electron, an electron cloud, we call this an electron cloud, and we'll get these green dots here, the density distribution. This electron cloud. Depends on how the electron cloud is distributed. And so we have different types of bonds. The types of bonds we're going to cover are, one is an ionic bond, two is a covalent bond, and three is a metallic bond. Ionic, covalent, and metallic. Those are the three we're going to look at. The first one we're going to look at are ionic bonds. Ionic bonds are just the attraction between a positive cation and a negative anion. That's what an ionic bond is. So if we have a plus being attracted to negative, that's basically it. And so let's look at the formation of ions first. The formation of ions we can understand based on something called the octet rule or the duet rule. So let's take a look at nitrogen here first. If we look at nitrogen, nitrogen is in group 5. Group 5 has how many valence electrons? Well, group 5 has 5 valence electrons. Group 5A are 15, which we are to look at. Those 5 valence electrons can be represented by 5 dots. Two of the electrons are paired, 3 of them are single. We like to have like 4 regions around here. Each region will have a mass of 2. And if we look at the electron configuration, we see 1s2, the core, helium core is filled, first shell is filled, and the valence shell will be 2s2, 2p3, which is going to have 2 plus 3 is 5 valence electrons. That's what we see. Now, when we do this, we don't distinguish between the S and the P. We'll just group them together. It's just in the highest shell, with the highest shell, and this 2 here. In order, basically, what we're going to do is we're either going to get rid of the valence shell or we're going to add some electrons here to fill it. And so, in this case, it'll be easier to add electrons than to get rid of electrons. We could get rid of, if we get rid of them, how many electrons total do we have to get rid of? 5. And so what's the charge range, the oxidation state range for nitrogen? Nitrogen varies from +5 to -3. Nitrogen's oxidation state is going to range from +5 to -3. And so if we look at nitrogen with +5, that's like nitrate. Nitrogen here is +5, the oxidation state. If we go to -3, that's like nitride ion. Oxidation state on nitrogen is -3. And then we can have, nitrite and NO and everything in between here. So not everything, but a lot of numbers in between here with these two. And so these are the limits here. The oxidation state. Nitrogen has a really rich redox chemistry because there are a lot of oxidation states available in nitrogen. But one of the ions that it formed, it seems like it would be good if nitrogen can gain 3 electrons. If it gains 3 electrons, then it fills the first shell and it fills the second shell. So the second shell is complete. When the second shell is complete, it has 8 electrons. Now 8 electrons will be considered an octet. And so it would be nice if nitrogen gained 3 electrons or 3 dots here. And so nitrogen should be an oxidizer. It's not a very powerful oxidizer, but it should be an oxidizer. It's not like fluorine or oxygen. It's kind of weak. In fact, we're breathing in nitrogen right now, and it's pretty inert. doesn't really do anything. If you tried to burn something in nitrogen, let's say there was no oxygen. If there's no oxygen and you tried to burn in nitrogen, would it burn very well? No, it wouldn't burn at all. I mean, nitrogen can be used to extinguish fire, so it's not a very good oxidizer. But nonetheless, if it did gain 3 electrons, we would see 8 valence electrons here. We write it in 4 regions. 1, 2, 3, 4 pairs of electrons. This is called an octet of electrons. That would form nitride with a 3- charge, or N3- would be the formula for that. So we end up with 10 electrons total for an octet. And so 10 electrons is the same number of electrons as what? Noble gas? Neon. And so we say that nitride is isoelectronic with neon. Well, neon is very stable, having that filled first shell and second shell. First shell takes 2 electrons, second shell takes 8 electrons, so it's a total of 10 electrons. Oxygen has 6 valence electrons. Oxygen is a more powerful oxidizer. It only needs 2 electrons to complete its outermost shell, complete its valence shell. And so if it gains those 2 electrons, and oxygen's a pretty decent oxidizer, you can gain those 2 electrons to form oxide. Oxide has an octet of electrons. It's filled valence shell now, and an octet with 2- charge. Here's the formula: O2-. 8 protons, 10 electrons. 8 protons, 10 electrons is going to give us the 2- charge. And altogether, it's going to have 10 electrons now, which is isoelectronic with neon. Iso, just the same electron, same number of electrons. Fluorine. Fluorine is the most powerful oxidizer on the periodic table. Also on our redox chart, it's the most powerful oxidizer, but there are more powerful oxidizers than fluorine around. Fluorine just needs 1 electron to complete its octet. It has 7 valence electrons, so if it gains that 1 electron, it'll form fluoride. Fluoride's got that octet, 10 electrons, isoelectronic with neon. It's fluoride. This is called the Lewis symbol, or Lewis structure for fluoride. Let's go on here. Neon. Neon is a filled first shell, filled second shell. Neon is unreactive. It's pretty much inert. It doesn't want to lose electrons. If it loses electrons, it's going to disrupt the shell, make it less stable. And it doesn't want to gain electrons. If it gains electrons, those electrons have to go in the next higher energy levels, or energy shell, which would be 3s. And it's going to destabilize things as well. So neon's pretty unreactive. It doesn't want to gain, it doesn't want to lose. Sodium. Sodium has a filled first shell and second shell. And so it only has 1 valence electron, the 3s1, so we can show that as 1 dot here. If sodium loses that 1 valence electron, then we have this filled shell configuration. So for sodium, it's more likely, it's got a low ionization energy, so it's more likely to lose that electron. It loses that electron to some oxidizer, and we end up with a sodium cation. The sodium cation is very stable, it's unreactive. Sodium cation really doesn't want to lose, it doesn't really want to gain. It doesn't want to lose to form a sodium 2+, it doesn't want to gain, let's go back to sodium metal. And so it has 10 electrons. 10 electrons, well, let's isoelectronic with neon. It's got that octet on the outer shell. 11 protons, 10 electrons. Magnesium has 2 valence electrons here, both in the 3s. So if it loses these, then we're isoelectronic with neon again. We have that octet. So magnesium 2+, is stable. Aluminum, 3 valence electrons. If we lose all 3 of those, then we'll have 10 electrons. So everything goes to 10 electrons in this. It's just going to go to the nearest noble gas. It's not always 10 electrons, because it's 18 electrons. look at the periodic table, we can see. What we should do. Well, if we look at these, for example, neon. Now, we want the goal here is the 10 electrons. So nitrogen, oxygen, fluorine are going to gain. And then over here, sodium, magnesium, aluminum are going to lose. Now, silicon's halfway. It might lose 4, could be like neon, or it could gain 4 to be like argon. Now, phosphorus wants to gain 3 to be like argon, sulfur gain 2, chlorine gains 1 to be like argon, which is 18 electrons. Potassium, calcium, scandium are going to lose 3. I mean, 1, 2, and 3 electrons to be like argon. Gallium can also lose 3 because the D10. D10 is filled in gallium. So we aren't going to lose any of these electrons. It'll just be the valence electrons there. Germanium's kind of halfway. Germanium can lose 4 to be like argon, or can gain 4 to be like krypton. Arsenic will gain 3 to be like krypton, selenium gains 2, bromine gains 1 to be like krypton. Whereas rubidium, strontium, yttrium, those will lose. Indium will lose, antimony will lose. These guys are like yttrium will lose one of the Ds, but we'll lose some of the Ds depending on where we are positioned. So the D complicates things. All right, so what happens? Well, we form the ions. Why do we form the ions? We form the ions so that we can form ionic bonds. Ionic bonds are stable. You know, the ions alone aren't necessarily going to be the most stable. Here we can see the ions. This is pretty much from the periodic table. Write the electron configuration of calcium with noble gas. Its ions isoelectronically. For calcium, we could just use the periodic table to do that. Let's take a look at the periodic table. Calcium will be, what's the nearest noble gas of calcium? Argon. So if we did the abbreviation, it's easy. It would be argon, and then what? S2. You can just count it from the top. It would be 1s, 2s, 3s, 4s. 4s1, 4s2. So argon 4s2. That would be calcium. Now calcium has 2 valence electrons. If calcium loses those 2 valence electrons, we end up with this. We put square brackets around here. Where this is a Lewis. It's a Lewis symbol. Then we have 2 electrons, or there are 2 dots. Okay, now what is the electron configuration for calcium? It would be argon. Argon is what? 1s2, 2s2, 2p6, 3s2, 3p6. So we could write it out. 1s2, 2s2, 2p6, 3s. Oh, this is wrong. What's missing? Argon is 1s2, 2s2, 2p6. Comes after 2p6. 3s2, 3p6, 4s2. So up to here is argon. That's wrong. The calcium ion is going to lose those 4s valence electrons, and this is correct, which would be isoelectronic with argon. All right, ionic bonds are held by the electrical attraction between the cation and the anion. Nearly all ionic compounds are solids. In fact, pretty much all the ionic compounds that we're going to encounter are all solids at room temperature and room pressure. And when we form ionic bonds, we form lattices, because we just try to put the ions together. So let's take a look at the formation of ionic bond here in different ways. Ionic lattices are very strong, which is why the compounds are solid at room temperature. They're also soluble in water. They have high melting points. Let's look at the reaction between sodium and chlorine. So what they did was they put some sodium metal there and some chlorine gas. So what's happening in that particular reaction? We can see this reaction in the video. This is making table salt from the element here, sodium and chlorine. They put some sand there so that there's much thermal shock to this, and they're generating some chlorine gas in the. That's some sodium metal they have on the cutting board there. This is being done in the hood, it looks like. A little audio here. Okay, so this purple stuff here is potassium permanganate. And potassium permanganate, what do you know about potassium permanganate? What one chemical property stands out most about potassium permanganate? Have you seen potassium permanganate in anything? No. Well, next week we have our test. The test is going to focus on what type of reactions? Redox reactions. Has anybody looked at the redox chart recently? I didn't. Redox chart, it's helpful to look at it once in a while. Most people don't. And so you'd have a tremendous advantage if you're one of the few that do. But there's lots of different redox charts. Like this one here. This is just one I just randomly grabbed off the internet. But what's at the top left? Fluorine, which is what? Powerful oxidizer. What's below fluorine? This is different than our chart because number 2 on our chart is different. Number 2 on this chart is cobalt 3. Cobalt 3 ions are a powerful oxidizer. Cobalt doesn't like to be +3. It'd much rather be +2. Number 3 is hydrogen peroxide. Number 4 is permanganate. Permanganate is a very powerful oxidizer. Now, we just talked about manganese yesterday. What did we say about manganese yesterday? What did we say about manganese yesterday? we're talking about the transition metals. Does anybody, what you want to do is kind of say, okay, what was the whole point of this? Is there any point to talking about the transition metals? What was the point of all that? If you wanted to come up with like a take-home point, what was the take-home point of talking about the transition? If you could come up with a take-home point, look at what an advantage you'd have. You'd be setting the curve in the class. And is it hard to come up with a take-home point? Not really. I mean, if it is hard, then you ask. You ask the teaching assistant, you ask the teacher, or you ask somebody, what the heck was I talking about during this time? Was there was it totally pointless, or was there some point to it? We're talking about the charges. Like +2. +2 is a very common charge on transition metals. Why? Because all of them have 2 valence electrons. The 4s2 in the first row. 2 valence electrons. And then sometimes we could lose some of the d electrons, right? We lose all the d electrons and all the s electrons of manganese. What's the charge? If we lost all the d electrons and all the s electrons of manganese, the charge is +7. And so we were looking at the charge, like for example, vanadium is +2, +3, +4, +5. Do you recall? Did I talk about that? Chromium was +2, +3, +4, +5, +6. Chromium +6. Manganese went up to +7. And so where do we see manganese in +7? We see it in permanganate. The oxidation state of manganese in permanganate +7. That's a lot of electrons to lose. So it's very powerful. And then these were all 8. And then we had 1, remember, copper and zinc, cadmium. Those are all, this is 1 and then 2 max. And those should be the max. So permanganate, yeah, this is a very, very powerful oxidizer. Now, what they're going to do is they're going to put some HCl in here. So this permanganate aqueous in aqueous solution. It's kind of messy. It's like grape juice. It's grape juice. That's what it is. It's been messy here. Some splatter. It looks like there's some solid, but this is aqueous potassium permanganate down here. Now what they're going to do is they're going to put HCl. And so potassium permanganate is a powerful oxidizer. And so what will it oxidize in HCl? What can it oxidize in HCl? I mean, there's already water present, so it's not going to oxidize the water because it's aqueous potassium permanganate. And so what can it oxidize in HCl? No. Do you have it in your notes when we talked about the chemical properties of HCl? You have a chance to look at that? Test is coming up, so we want to start reviewing your notes and get any questions answered that you have questions on. We discussed the chemical properties of HCl, metathesis, acid base, and redox in detail. I don't know how many minutes I spent on it, but have you had a chance to even look at it before the test? Because ideally, if you want to, I know this last test might not have gone so as well as you would have hoped, but this next test, hopefully it'll go better. Well, how can it go better? You want to make sure you're well prepared. Being well prepared is understanding everything we talked about. Wow. if you understand everything we talked about and you can do the homework problems, then you're going to be well prepared. You're going to do very well. You should. Well, the steps in getting well prepared is just to be able to, reiterate or regurgitate, Like if I go down and I list all the chemical properties of HCl, the first step is just to be able to repeat that. Repeat it by just following the same pattern in the answer as I did. And then you pick a new one, like say rather than HCl, we pick nitric acid, HNO3, and then do the same thing with that. Then you have a good understanding if you can apply it. And the first step is to understand it, and then the original one, and then apply it. It can't oxidize the hydrogen because the hydrogen's already been oxidized. The hydrogen is H+. And hydrogen only has one electron. If we look at hydrogen, hydrogen has one electron, one valence electron, and it's 1s1. If we lose that one valence electron, then we'll form H+. That electron will go somewhere. And now, what's the electron configuration for hydrogen? Well, it's 1s0. We have no electrons. And so how can a hydrogen ion be oxidized when it has no electrons? There's no electrons to oxidize because the electron's already gone. It had one electron, it lost it, it made H+, and now it has no electrons. And so in order to oxidize hydrogen, it would have to have an electron to oxidize. It doesn't, so we can't oxidize it. However, we could oxidize chlorine. It's not chlorine, it's going to be chloride. Chloride doesn't want to be oxidized because it has an octet. And so it's very hard to oxidize chloride because it's got that octet. And so chloride is one of the weakest reducing agents on the chart. If we look at the redox chart, where's chloride in terms of reducing agents?
Top right.
Yeah, top right. It's one of the weakest reducing agents. It's just a little harder to oxidize, a little easier to oxidize than gold. Whereas the best reducing agents are at the bottom, like lithium, is way down here. Chloride's very hard to oxidize. Why? Because it's got this octet. It doesn't want to ruin that octet. And so in order to oxidize chloride, we would need a very powerful oxidizing agent. Now, is permanganate powerful enough to oxidize chloride? In other words, do you remember the pattern that we did? Tell me everything that will oxidize chloride. We did this actually in class. We listed everything that would oxidize chloride. Do you have it written in your notes? What is everything that oxidizes chloride?
Stronger than chlorine.
Yes. Anything stronger than chlorine. And so what is stronger than chlorine? Well, we need an oxidizer that's stronger than chlorine. So on this chart, gold 3 ions would oxidize chloride. On this chart, permanganate in acid will oxidize chloride. Hydrogen peroxide in acid will oxidize chloride. Cobalt 3 will oxidize chloride. Fluorine will oxidize chloride. But will dichromate oxidize chloride? No, dichromate, chromium's in the +6 in dichromate. This is called chromium 6. Dichromate and chromate are both +6. This chromium 6 has a checkered history. Chromium 6 in California. In California, there was some well water that was contaminated with chromium 6, and people were drinking it and suffered from high rates of cancer or whatnot. And they made a movie. There's an activist there. Made a movie about her, about the chromium 6 contamination in drinking water. Well, anyway, chromium 6 is not powerful enough to oxidize chloride. Oxygen is not powerful enough to oxidize chloride, etc. Do you recall doing this kind of stuff? You should start reviewing it now, you know? Absolutely, start reviewing. Because, you know, we got time now because the test is going to be in a little over 1 week. And so we got time. If you look at it every day from here till the test, you'll be in a much better position than if you just wait the night before to look at it. You know, look how much stuff is forgotten. It's so easy. I just saw some thing online yesterday. It showed a brain, you know. It showed 30 minutes after, 100% of the knowledge was retained. It was like 2 hours after, like, or something like that. They showed just 40% of the brain. So it's like, if you forget 60%, that's 60% of the time totally wasted. You know, you might as well just go off and have a vacation. But sometimes I think of that too. You know, if you forget it, you might as well just go play video games and do something else. You know, well, what's the use of sitting here if you're going to just forget it? Well, anyway, so the test on the reactions we're going to focus on next week are redox reactions. This is a classic redox reaction. This reaction is very well known. This reaction is known to generate chlorine gas. And people use this reaction all the time to generate small quantities of chlorine gas in the laboratory. And to generate that, all you do is you put some potassium permanganate and then just slowly add some hydrochloric acid to this, and the potassium permanganate will attack the chloride, oxidize it to form chlorine. And then that chlorine gas, that green gas, they're going to put in here with the sodium metal. Let's take a look at what happens with this.
And you know this chlorine gas is present when you see a yellow.
The audio is pretty bad with this.
Here that I gave previously, I'm going to pump it up. Well, I can speak with some acid or hydrochloric acid. Chloride ions reacting with manganese ions. When the chloride ions reach the negative for the electron,
Well, we can.
you force them oxidized by the presence of oxygen.
I'm just going to get rid of the oxygen. So here they're putting the hydrochloric acid, looks like, and they pour the hydrochloric acid in there. You got to be careful sometimes. Well, what is that? Is that zinc? Zinc night? No, there's something wrong with that label. Should have grabbed a different video. Pour the hydrochloric acid in there, and then it's going to start generating a yellow-green gas. Green-yellow gas. The bottle's mislabeled. Obviously, should have on a different video. That's so common. I could have just grabbed another video. Okay, let's fast forward. The reaction's slower. It's not explosive because chloride is such a bad reducer. If it was a good reducer, you'd have an explosion. Actually, maybe this is a different reaction they're doing to generate it. Looks like they're putting some other stuff. All right, so here you can see the flask is filling up with chlorine gas. A piece of sodium metal. Reaction starts off slow. Reactions with solids always start off slow. But they're very deceptive because they start off slow and then increase exponentially. This is why so many places have unexpected explosions, because it doesn't seem like it's reacting, and then as the temperature creeps up, then things can get explosive. So that was a very quick reaction. But it was a very slow start initially. And that's typical of how these things react. It takes a long time. I've had to fast forward it, but once it starts going, then the temperature increases, and when the temperature increases, boom, it gives this exothermic reaction. You put a little bit of water to get it started. Okay, and then let it cool down, and then you have salt crystals. So I should have got one more video. I have a better video demo from that one from Berkeley. Search for it. Okay, so what we're going to do here is we're just going to look at what's happening. Using Lewis structures, Lewis symbols. So sodium has one valence electron, and the electron configuration for sodium is going to be neon 3s1. And then chlorine, what I'm going to do is I'm going to split the molecule. It likes to form diatomic chlorine. What I'm going to do is I'm going to form atomic chlorine like this. And atomic chlorine is going to have the electron configuration. What is the electron configuration for atomic chlorine? Let's see. It's going to be neon, 3s2, 3p5. All right, then what happens is the oxidizer comes along, and the oxidizer is going to take the electron from sodium. So chlorine wants one more electron, takes the electron from sodium. So then we end up with this. We're going to end up with sodium with no valence electron. So Lewis structure would look like this. It would be sodium like this, and the electron configuration for this would just be neon. And then chlorine will have a complete octet now. It'll be like this. And the electron configuration for this will be argon. Correct? Yeah, it'll be argon. It'll be next to that. So this is called the Lewis structure for sodium chloride. Now, it doesn't form molecules. This is what we call the ionic bond. The ionic bond is just having the two ions next to each other. And it's not shown in any special way. It's just having the ions adjacent to one another. When we look at this, though, when we look at sodium chloride, all ionic solids are like this. We have a positive ball. Now, sodium ions, what happens with the size of the atoms, it shrinks. And so what's bigger, sodium or chlorine? This is a sodium atom versus a chlorine atom. If we take a look at the periodic table, what is bigger, sodium atom or chlorine atom? Did I talk about the size trends yesterday? No?
In relation to like the orbital, like 2p versus
Yeah, I think I forgot to do that. We talked about the size trends. Size trends like, what's the biggest? Do you know what the biggest atom on the periodic table is? What the smallest atom is? Yeah, I didn't make it through that. Do that. Forgot to do that. If we look at the biggest atom on the periodic, at least the biggest atom, what do you see as the biggest atom here? I see this one. What is this one? CS, which is called cesium. Cesium's the biggest. What's the smallest? Looks like the smallest is up here. Oops. What is the smallest? Helium. Helium beats hydrogen. If you look at this is 31, that's 37. So helium just beats hydrogen. But helium's the smallest, cesium's the biggest. Now the question comes up, why is helium smaller than hydrogen? I'm going to come back to this, sorry, mixed up here. But if we look at hydrogen, hydrogen consists of one proton and one electron, one s orbital. Helium consists of two protons and two electrons. So shouldn't helium be bigger than hydrogen? It's got more stuff. If it's got more stuff, isn't it bigger? You would expect it to be so. But it turns out that helium is actually smaller in size. Now, why is it smaller in size? The reason it's smaller in size has to do with this. What's holding the electron to the nucleus? Well, it's an electrical attraction between the positive nucleus and the negative electron. Electrical attraction. And the same thing here in helium. What holds the electrons to the nucleus is the attraction between the positive nuclear charge and the negative electron charge. Now, these two electrons are in the 1s orbital. This electron is the 1s orbital. Now, hydrogen and helium don't have the same size of 1s orbital. The 1s orbital on helium is actually smaller. Why is it smaller? The reason it's smaller is because of this. The two electrons want to stay away from one another because both of them have negative charge, so they try to stay away. And so when I look at this one electron here, this electron sees the nucleus. And when it looks at the nucleus, it sees a +2 charge. This electron, when it sees the nucleus, it sees a +1 charge. And so what's a stronger attraction, a +2 or a +1? A +2. And when we look at this electron down here on the bottom, it sees a +2. And so both these electrons see +2, which means that the electrons are going to be pulled in closer, like a tractor beam in science fiction. And over here, this one's going to be just here. And so this electron can get further out from the nucleus, however these can't. And so the 1s orbital on helium is smaller, and therefore this atom is smaller than hydrogen. And so as the charge increases, the charge in the nucleus increases, it pulls the electrons in closer. And so that's what's happening here. If we look at the next shell, in the next shell, as the charge on the nucleus increases, we get more and more protons. What happened? The atom shrinks down. And so here, it's because of increasing nuclear charge, increasing positive charge in the nucleus, the atoms get smaller. And so as we go from left to right, atoms get smaller in the same shell. However, what's going on here? And so, like hydrogen has 1 proton, lithium has 3 protons. Why is lithium bigger? You know, if this is +1, this is +3, shouldn't +3 be even stronger than helium and pull everything in closer? And the answer is yes, it does. And so if we look at lithium, lithium is +3. And so if I look at the 1s orbital on lithium, the 1s orbital on lithium is even smaller. It's even smaller because those electrons, lithium, those electrons are going to be attracted to +3 rather than a +2. So it's going to be smaller. And so lithium is going to have the smallest 1s orbital out of these 3. However, lithium also has a second shell. And that second shell is the 2s orbital. And so the 1s, the 1s is smaller, but the 2s, we add another shell, and the 2s is going to be big. And so The reason why, even though we have more protons, we add the shell. So from hydrogen to lithium, add a shell. Lithium to sodium, we add another shell. We're third shell now. Sodium to potassium, we're in the fourth shell. We added a fourth shell. So each time you add a shell, it grows bigger. Shell of electrons. But once we stay in the same shell, we're not adding a shell here. So if we're in the fourth shell and we don't add a shell, we just add protons. As we add protons and electrons, it contracts. The size contracts. And so the size trend goes like this. If we look at the periodic table, then the size decreases, decreasing size, because increasing number of protons. And if we go down, the size increases because of increasing number of shells. And therefore, the biggest atoms are going to be at the bottom right and the smallest at the top. Bottom left, biggest atom, bottom left, and the smallest atoms at the top right. And so what's bigger, sodium or chlorine? Sodium's bigger. It's in the same shell as chlorine. Chlorine has more protons, so sodium is bigger than chlorine. Good. Sodium is bigger than chlorine. And so chlorine's going to take an electron from sodium. Sodium's easy to take an electron off of. Taking an electron off an atom is related to something called ionization energy. And I need to talk about that briefly. So this is atomic radii, that's what we're looking at. Now let's just do an example of atomic radii. Refer to the atomic table and list the atomic numbers 15, 16, 33 in order of increasing size. So let's look at the periodic table and look at elements 15, 16, and 33. So element number 15 is phosphorus, 16 is sulfur, and 33 is arsenic. So let's start off with phosphorus. Phosphorus versus sulfur. Which one is bigger? Phosphorus is bigger. Sulfur is smaller. Same shell. More. Phosphorus versus arsenic. Arsenic's bigger because additional shell. And so the biggest will be arsenic, followed by phosphorus, followed by sulfur. So both sulfur is the smallest. So that's what we see here. It goes sulfur, phosphorus, arsenic. All right, when we ionize sodium, that is when sodium loses an electron, it's related to the ionization energy. Sodium's easy to oxidize because it has a relatively low ionization energy. So let's take a look at ionization energies. Ionization is the energy required to remove one electron from a neutral gaseous atom. So we're removing one electron from sodium. Chlorine's doing the removing here. Ionization energies. First, we're going to look at ionization energies related to the periodic table. But here we have sodium. Sodium's going to lose that electron. Chlorine's going to take it. And then we're going to end up with a sodium ion. This is called the first ionization energy. If we look at the ionization energies follow the size trend. And so let's go back to the size. What do you think is going to be easiest to ionize, or easier to ionize? Sodium or cesium? We're going to take one electron away. What do you think will be easier to remove the electron? Sodium or cesium? Cesium. Cesium, because it's bigger and the electron's further out. The farther the electron is away from the nucleus, the easier it is to strip off. And so the ionization energy for cesium is even easier, but sodium's still fairly easy. In fact, all these are easier to ionize because these are all kind of bigger atoms. As we go to the right, these become much harder to ionize. And so the alkali metals are the easiest to ionize because they're the biggest atoms. And so ionization energy follows the size trend. The hardest, what do you think the hardest element to ionize is? Helium. Helium by far is the hardest to ionize. Cesium would be the easiest to ionize. And so it's just going to follow the size trends we see over here. This is energy on the y-axis. The hardest to ionize is helium. And so what's harder to ionize, hydrogen or helium? Helium. Helium is smaller. If we look at the alkali metals, all the alkali metals are kind of big. So lithium is easy to ionize, sodium is easy to ionize, potassium is easy to ionize. So if we start off, the first shell, we have hydrogen versus helium. In the second shell, we got lithium versus neon. And so we go lithium. And then beryllium. Beryllium's harder to ionize because it's smaller. And then we go to boron. Boron is smaller, but there's a little blip here. Boron should be harder to ionize because it's smaller. It turns out that boron is a little bit easier to ionize because we're ionizing, rather than an s electron, this would be 2s, 1 electron, this would be a 2s, 2 electron that we're ionizing. This is a 2p, we have a 2p one, so it's easier to ionize a p electron than an s electron, so there's a little blip there. These little blips can be explained quantum mechanically here. Carbon's smaller, it's harder to ionize. Nitrogen's smaller, it's harder to ionize. But oxygen is smaller, and it should be harder to ionize, but it's easier to ionize. The reason oxygen is easier to ionize, you don't have to have these memorized, because in nitrogen, we have a half-filled P. So when we ionize this, we're ionizing one of these P. In oxygen, we have more than a half-filled P. So when we ionize, we're ionizing a paired electron versus this unpaired electron. The paired electron is easier to ionize because we have 2 electrons in the same orbital, and the 2 electrons like to stay away from each other. They both have the same charge. So if this one leaves, then this one will be happier in that case. And so in this case, oxygen is a little easier, and then we're back. Chlorine's paired, neon's paired, so it becomes harder. So as we go across the shell, it's harder to ionize because it's smaller. This pattern is repeated here, basically. And so all you have to know is it just follows the size trends. These little blips we can explain. The same thing with little blips in the size. The little blips in the size, like here, like thallium, lead, bismuth, polonium, you're bigger. This is a P1, P2, P3, so we have half filled. Now we've got a pair. And pair size one up a little bit. And the P4. All right, let's take a break and then we'll finish the sodium chloride example here.